Hey, hi. Thank you all for joining. Quite a crowd. In this talk, we are going to share with you what you'll learn about analyzing DNS requests generated by mobile devices. As our data shows, it seems that DNS is quite an interesting resource that can be used to build user device profiles and then to track user devices across different network contexts. This is a high-paced talk. We also have a couple of equations along the way, but we'll get them through really quickly. We also have a white paper accompanying this presentation, so you can check it out for additional details. My name is Jan Gabela. I am a senior security researcher at Bitdefender. I work on IoT security and vulnerability research, but at the end of the day, I'm a scientist.
Hello everyone, my name is Ioan Pădurean. I am a junior security researcher with key focus on applied machine learning techniques and IoT security.
We come from Romania, from a region called Transylvania, so it's what's quite a flight, and we are happy to be here. Let's see what's on the agenda. We'll kick things off with an introduction and motivation of our work. Early on, we are going to look at the data and show you key differences between key platforms that we have analyzed, iOS and Android. And then we are going to dive into some data analytics, performing some request patterns and transformations. And then we'll get to the fun part. We'll see how we can use DNS traces in order to perform user tracking by leveraging very simple statistics. And if there are any machine learning fans in the cloud, that's great. We are going to also show you how we can apply machine learning techniques in order to perform user tracking. At the end, we'll end with conclusions and key takeaways. Now let's see how it all got started. So I think that everybody knows about the domain name system. We use it to translate domain names to IP addresses. The most important thing is that all devices rely on DNS. So it's very important that this resource functions properly and it's not being misused. Now, while having exceptional role in enabling our internet, DNS also plays critical functions in delivering security applications. So if you work for a security company, you know that you can harness DNS in order to develop a wide range of technologies, such as parental control, spam filtering, ad blocking, and so on and so forth. You can also do IoT security by using DNS. So it's quite a valuable resource, and there is a lot that is being invested into using and harnessing DNS for various purposes. Now, why yet another research on DNS? This was not on purpose, so we're not really looking for ways to track users. No, we are actually looking for ways to improve our security solutions. So we're looking at different approaches for improving parental, spam filter, the basic security technologies. And at one point, we started to look at network traffic that was being generated by devices. And we were starting to see the same DNS requests that were being issued by devices. And without having to use any fancy AI tools or analytics, by looking with our naked eyes, we were seeing the same DNS requests and the same sequences and patterns that were being generated by devices. So we thought, OK, if we are seeing these repetitive sequences with the naked eye, wouldn't it be possible to build user device models and then use these in order to identify devices across different networking contexts? So this was a question that we popped early on. And the more we thought about it, the more we realized that, yes, this could be possible, but we're not quite sure about the accuracy of the approach. And we have seen that nobody really has done a thorough analysis and research in this topic in the field. So we thought, OK, why not? Let's try and do a research in this direction. But before diving into the topic, we should step away behind and look at the privacy-related policies that we have, because we have OECD, we have GDPR, we have also the EU always making up new rules and regulations. Everybody is getting quite paranoid nowadays and trying to hide data. So how is this possible? So despite these aspects, as we are going to show you in this talk, we are still able to identify this relevant data and use it for our purposes for user device tracking. Now, we should also mention two technical privacy measures that are in place in order to explicitly prevent user device tracking. We have the MAC address randomization, right, which is aimed to generate a new identifier for devices such that it's no longer easy to associate devices with data that's what generated by devices. Now, this raises the bar for tracking. We now have a time limit in which we need to aggregate data and use it for building these user device profiles. However, as we know it, many devices still use the same MAC address while connected to the same network, and this time limit, as we are going to show you, is sufficiently large so that we have enough DNS requests so that we can build these rather interesting profiles. Now, the second technical privacy measure is the secure DNS, which basically means to encrypt DNS requests. Now, this is a major improvement, and it eliminates local snooping capabilities. So if you are on the same network, you're no longer able to capture DNS requests. They are no longer sent in plain. So this is very good technology. However, it is not as widespread yet. At the end of the day, you're still relying on a DNS resolver, which may play the role of the curious DNS resolver. So you're, okay, not using your local DNS resolver, but you're handing over your DNS request to another resolver that may also play this curious role. So at the end of the day, how much time do we have in order to build these profiles? Now, if we take just a very simple setting, the iOS Wi-Fi default setting, we can see that for rotating MAC addresses, we can have 2 weeks of a timeline, and this gives us a very rough timeline that we can consider in our research. So if we are able to build these patterns, if we are able to aggregate these traces in less than 14 days, then we will be able to build the profiles and perform user device tracking. Now, if we agree that we are handing over all this data to telcos, can we trust them not to misuse our data and use it for other purposes? Well, we need to look into the past. We have seen in the past, unfortunately, in several cases that telcos have handed over our data to governments, have handed over our data for other entities, and also performed targeted advertisement without explicit user consent. So this has happened in the past. So if we project it for the future, for sure, we can say that there will be a temptation also for the future to misuse data. Therefore, we need to take measures, understand the problem, and ensure that will not happen in the future. One last question in this introduction: how new is this research? When we first started, we were hoping, to be very new, to be groundbreaking. It was not the case. When we checked the state of the art, we have seen quite a few studies on this topic, harnessing DNS requests for user behavioral modeling. However, we still have several key distinctions. To the best of our knowledge, this is the first study with exclusive focus on smartphones. We also have a larger pool and more relevant set of devices. And we also provide key insight that are specific to popular platforms nowadays, iOS and Android. And at the end of the day, I think that we can all agree that the smartphone is the most important device that can be used in order to track users. I mean, we use our phones for everything, for work and productivity, for shopping, for communication, health and fitness, and all of these come with their own applications. You install apps, and they start to generate DNS requests as you install them. And if someone harnessed these DNS requests, then we have a profile of your device, which can be identified later on in different networking contexts.
Let's take a deep dive into our research and see how it was structured. For this research to be relevant, we had to play the role of the curious DNS resolver. At Bitdefender, we have a bunch of security solutions that rely on our own DNS resolvers. After figuring out the necessary privacy measures such as hashing device identifiers, so there was no way we could trace back a device's hash to its MAC address, we tapped into Bitdefender's DNS resolvers and registered to the events of approximately 30,000 devices. We collected about 35 days worth of data and obtaining at the end 985 million events. We used 4 computational clusters and totaling 80 virtual CPUs and 1.5 terabytes of RAM. We are curious about the distribution of DNS requests, and for iOS, United States dominates this field. For Android, we can see a difference not only in the number of countries, but also not only in the number of requests, but also in the number of countries. Significantly fewer countries were found, with France and USA dominating the number of requests. Nevertheless, in both cases, for both iOS and Android, DNS requests have been collected from all over the globe. Let's take a look at the data in terms of number of requests. One versus the other, we can see that iOS generates approximately the same number of unique domains as Android devices, but a lot more requests. This is especially visible in the right bottom, where you can see that iOS devices have a tendency to generate more requests than Android devices. By what amount? Well, by taking a look at the most common domains based on the number of devices that access it, we can see that popular platforms such as Facebook, YouTube, and search engines are present the most. If we take the operating system separately, we can see that iOS focuses mostly on Apple-related DNS, while Android focuses on Google and popular platforms. There is also like a 10 times difference in favor of iOS regarding the number of requests. We have seen the bird's eye view on the data. Now let's discover some of DNS request patterns that can be used for tracking. Up front, if we project the number of requests over 72 hours, we end up with this visualization. We have a selection of 16 Android and 16 iOS devices. For both Android and iOS, we can see that in many cases, maybe not visible to the naked eye, devices perform repetitive number of requests. An interesting aspect we realized early in our analysis was that by color coding the number of requests for each domain over 1 hour time windows, we can generate live images. There are a bunch of image processing algorithms out there, so if someone is passionate about this direction, just project DNS requests as images and you'll have a goldmine of data. The data set we obtained was realistic. The more we looked, the more domains appeared, and as we looked over time, we noticed grouping of DNS requests over days and weeks. We also had to deal with missing data, which was all the devices not sending a request to our DNS resolvers. Maybe they were not using our security products. And we observed the same patterns across all devices, be it Android or iOS. Okay, we talked about DNS, we have seen the patterns, but what is the best approach to use DNS requests in analytics? Early on, we realized there are two elephants in the room when it comes to processing DNS requests. We have to deal with categorical values, and there is a large amount of requests that needs to be processed. The first challenge that any analysis must tackle is how to deal with categorical data. Algorithms best work with numbers, not with strings. We have a selection of the most commonly used techniques: one-hot encoding, label encoding, and feature hashing. One-hot encoding generates a binary matrix, while label encoding assigns an index to each string in alphabetical order. On the other hand, feature hashing applies a hash function over the string, assigning a number for each distinct one. Unfortunately, by looking at all these encodings, we soon realized that they do not apply to our program. Each one comes with its own drawbacks, ranging from high dimensionality to hash collisions. We had to find a better approach. We are quite desperate. We are sitting on tons of data and struggling at finding an approach to give it a meaning. But we had an idea. Why not look at DNS requests as sequences of words in a document or a trace? After all, this idea is common in the field of natural language processing. By framing it to a trace comparison problem, we also found the tool to compare documents, namely term frequency, inverse document frequency, or in short, TF-IDF. TF represents the rate the words appear in a document, while IDF represents the rarity of the words across all documents. TF-IDF works well with strings. It quantifies the frequency of the words and highlights those that are rare across all traces. It also scales well because of usage on traces, and the risk of bias is low. So how does one interpret the value of TF-IDF? Lower TF-IDF value maps to higher frequency across all documents, or lower frequency in a single document. On the other hand, a high TF-IDF value means a certain word appears repeatedly in a few documents. Very quickly, to give you an example on how TF-IDF works, we have these three sentences. If we take a look at the words black, hat, and rocks, we can see that their IDF is lower due to them appearing in all three sentences. If we look at the TF-IDF, the value in the first and last sentences is lower than in the second one due to term frequency being lower, because these sentences have more unique words. These days, everybody uses AI for literally anything. As school kids who also met, we decided to first go the statistical analysis route. In the end, AI is a mixture of known methods, but we do not trust it to do our job better than we do. We like to have explainability for our results, and at the same time, one will most likely run into issues such as the explosion of parameters and exhausting available resources. We decided to keep it simple and maximize our ability to process a vast amount of data. There is some math related to our analysis, but we will walk speedily over it. You can later review it on the slides and our white paper. In terms of comparing traces, we chose cosine similarity, which handles very well high-dimensional data and compares the elements in traces and at their frequency. To give you an example, we have these two traces, one containing the words black hat and the second one repeated the words 3 times. By applying cosine similarity, we get that the two sentences are identical. However, if we were to apply different metrics such as the Euclidean distance, the numbers would yield that the two traces are different. Hence, the motivation for choosing cosine similarity as our metric. Our second challenge was with the astonishing size of the data. Just loading all the data for 30,000 devices takes tens of gigabytes of RAM. So we have 3 key parameters: the number of devices, the number of time windows, and the size of each time window, where a time window represents a trace constructed for a device over a given time interval. We also process the devices in batches ranging from 200 to 5,000.
Right, so we have seen how we can process these DNS traces. Now, let's see if we can use them for identifying devices and ultimately for tracking these smart devices. Now, if you think about it, we'll ended up having millions of DNS traces, and we're trying to associate these traces to devices. So it's something like finding the needle in the haystack problem, but we managed to boil it down to a matrix. So it's very important always to find the right mathematical construction and structure in order to frame your problem. In our case, we built a similarity matrix. Each dot in this matrix represents a similarity computed on 2 DNS traces. The brighter the color, the more similar are 2 traces. As we can see, we have special colors, very bright colors on the diagonal, where we have device self-similarity computed for several example devices, namely the similarity between traces taken from the same device. As we can see, colors are brighter because the traces are more similar for each device, and this means that these devices can be distinguished from other devices in this pool. So there is hope for this approach. Now let's boil down to the steps. We take the basic DNS traces, we split them up in time windows, depending on how much time you have aggregated traces for certain devices. You compute these indexes and then apply tracking index that we will define in the following slides. Now, we only have 2 equations here, so stay with me. We have the average self-similarity, which basically evaluates the consistency of a device's behavior with itself. So we have traces from the same device taken several times, and we evaluate how consistent are these traces, so we can distinguish this device. And then we also have the second equation, which evaluates a device's similarity to other devices in this pool. And if we take these 2 equations, we have a very simple mathematical third equation, right? Which is the tracking index. And this is computed by having the self-similarity from which we subtract the maximum co-similarity. And if this value is positive, it means that we can distinguish the device from the pool of devices that we have in our management. Now, if we take a very simple example, we have this self-similarity matrix in the middle. It has very nice bright colors, which means that the traces are very similar to each other. So the device has a more or less consistent behavior. And we compute the self-similarity index, which has a value of 0.34. Now, if we compare these traces to traces taken from other devices, we see that the colors are not that bright, which means that the similarity is lower with other devices, namely 10 times lower. So in this pool, we have a very trackable, distinguishable device, and our tracking index is positive, which is great. Now, let's take all of these concepts and put them into practice. At first, we have taken batches of 250 devices, iOS and Android separately, and we also considered a mix of iOS and Android devices, as you would normally find in real-world scenarios. Now, as we can see here, time will heal not only wounds, but also our tracking accuracy. So the more time we waited, the more we aggregated, the better for our tracking accuracy. This means that the more you stay online with the same identifier, the more DNS traces you will generate, and this will improve and have a positive impact on the tracking accuracy. After 2 hours, as we can see here, we have reached a staggering accuracy, I believe, above 80%, which is very, very good. And we topped out at 96%, which is excellent. Now, what this means, changing our identifier is good to give as less time as possible in order to associate traces to a certain device identifier. Now, let's take it up a notch and see if we have batches of more devices. If we have 5,000 devices, how does this impact our tracking accuracy? As we can see, if we have more devices, yes, this will have a negative impact on our ability to identify devices. And nevertheless, after 24 hours of aggregated traces, we are still able to exceed 90% accuracy, which is once again very good. So yes, the crowded the better, the more devices are, the lower the tracking accuracy. However, even in this case, time is a very important factor. So if you stay more time online, the more you generate traces with the same identifier, the better the tracking accuracy.
At the end, we said, why not? We decided to give AI a chance and see if it can beat our statistical skills. Out of all machine learning algorithms, we decided to go with LSTM, long short-term memory. It is a type of recurrent neural network that uses a special cell in order to give the network some memory. It is used for speech recognition, time series, robot control, and many more fields. Since DNS requests can be seen as a time series, we said, why not use LSTM? The first trials were promising. We managed to reach 78% accuracy for a selection of 100 devices from each OS. So we thought that we can do better than this. But choosing the best architecture of LSTM may be hard. There are lots of factors. Optimizers, the learning rate, the random weight initialization, the number of cells, the combination of layers. The list goes on and on. We ended up consuming a lot of time not only in finding the optimal model, but also a model that could fit into our available memory, which was not small, but 400 gigabytes of RAM. As it turns out, we are unable to load data related to 5,000 devices and 3-hour time windows into our memory. We had to reduce the data size, that is, reduce the number of documents by grouping them in bigger time windows. After finding a data model that could fit into our available memory, it was time to dive into the never-ending problem of finding the optimal model. After many trials and errors, we managed to find the model that worked the best for us. One LSTM layer with 188 cells would do the job. We put a selection of LSTM models to the test, and surprise, the best test accuracy was around 96% for both operating systems. So we can track user devices by leveraging machine learning. Of course, with machine learning, there come certain issues. Training 48 models for each OS for 2,500 devices took around 280 gigabytes of RAM on iOS and 190 on Android. We used 2 computational clusters, 64 virtual CPUs, and a total of 9 days for both operating systems. So there is a limit in the data size, resources, and the searching the optimal model, which makes this solution difficult to apply. To summarize, there is a trade-off between the approaches we took for our research regarding the resources used and the accuracy score. While LSTM consumes more time and processing power, if you find a good model, you could have comparable accuracy or even exceed the accuracy of statistical techniques. On the other hand, cosine similarity is faster and needs less resources while having slightly lower accuracy, at least for the same number of devices. Before we conclude, we should talk about the money. By using the cheapest cloud provider, there will be a minimum of around $3,000 a month, so virtually anyone with minimal resources can build accurate user profiles and track their devices. But wait, there is more that we have learned in our research. Do you remember the large amount of DNS requests? Toward the end of our research, we thought, devices perform the same request over and over again. So do we really need all of those requests, or is it sufficient to have just enough to preserve their statistical distribution? We started to randomly drop DNS requests while measuring the impact on our tracking accuracy, and what do you know? By dropping 20% of requests, the accuracy stays the same, and by dropping around 80%, the devices are still fairly easy to detect. Of course, this information would have been awesome to know beforehand because we could save a lot of money, storage, and processing power. But this is now available for future research, so you can save tons of space by storing only a fraction of DNS requests.
Yeah, so let's see what we have learned and what are some key takeaways. Now, as we have seen, user device tracking, so building these profiles is relatively easily and cheap. And you can also achieve a very good accuracy that can increase above 95%. You can go for the statistical techniques which can handle more data. But if you like machine learning algorithms, we have only tried LSTM. However, there are a bunch of other techniques, algorithms out there, and you can try them and maybe achieve even better accuracy. Nevertheless, machine learning requires more time, more memory, more processing power, so it eats up more of your resources. But if you have resources, go ahead. Last important aspect is that we have only applied these DNS profiles for a single scenario. However, if you have accurate user device profiles, I believe that these may also expose users to other threats, including targeted commercials, placement of products, and so on and so forth. And I only have one last slide that shows you and details one of these possible applications. We have explored towards the end of our research a possibility to model user behavior and to see if we can detect major behavioral changes. For this purpose, we have taken a bunch of devices and data over 2 weeks. We have split up the data in 2 weeks, one versus the second week, and we have applied clustering and evaluated the quality of clusters using a silhouette scoring, and we have measured how this scoring changes from 1 week to the other for all of our devices. And as we can see in this figure, we can accurately identify behavioral changes. In fact, for the vast majority of devices, we have seen there are minor behavioral changes. However, we can very nicely identify outliers, which are practically major changes. And this can be tracked back to changes in applications. So if you install another application, it will generate other DNS traces. If you change your browsing preferences, maybe you get a notice, an email, just look another topic, you will have, therefore, changes in your behavioral profile, but also changes of location may also yield to different profiles. So at the end of the day, if we take these DNS requests, we can see that there is a huge privacy exposure and other possible applications and misuses for these DNS-based profiles. Now, as actionable items, we have identified here 3 items. We should go ahead and use MAC randomization, possibly making it more aggressive. Also, use encrypted DNS if available. It will help you. However, at the end of the day, we are still relying on DNS. I mean, many security technologies, but other technologies are relying on DNS, and it's important to inform the user, okay, we are collecting DNS to provide you these security solutions. However, right, we are not storing it. We are only storing it for this amount of time. We are anonymizing it, so we are taking all the measures in order to ensure that your data is not being misused. Now, if you are tech guys, great, you can also employ some technical measures such as DNS proxies. You can also aggregate DNS requests. Remember the 2 lessons, right? So these will help you in order to lose your identifiers. Now, last but not least, we'd like to say special thanks to the machine learning team at Bitdefender. They helped us a lot with developing some of the algorithms and techniques. Thank you.